Okay, I would like to revisit Faraday's law, and in terms of Maxwell's equations, which we've already discussed. And let me just focus in on the four integral equations. Oh, sorry, the three integral equations. There's a fourth. The fourth is currently E dot dl equals minus delta V. But that's sort of one doesn't look like the other. So we've got up in the upper left-hand corner, Gauss's law for electricity. In the upper right-hand corner, Gauss's law for magnetism. In the lower right-hand corner, Amperes Law for magnetism, for calculating magnetic fields from current distributions. And then in the lower left-hand corner, we've got just the definition of potential difference. Well, we can use Faraday's law in order to modify the definition of potential difference and make it look like the others. Now, let's just look at look at the similarities first, right? So you've got two integrals over area, electric field flux and magnetic field flux, and you got two line integrals, electric field dl and magnetic field dl. So there is some symmetry here, but we can use Faraday's law to make this equation look like that equation for the magnetic field. So let's just think about the fact that Faraday's law tells us that a potential difference, right? So this is a delta V, but it's just a different way of writing potential difference, is equal to minus the change in flux, the change in time. You might say, where's the N? Well, the N can be encompassed in the flux, right? The flux can be B times NA, or it can be taken out. We've been taken out before. We can just talk about for a single loop. We could just use N equals 1 or encompass N in the flux equation. So we can just write that without N. So let's just say we have a single loop, and we've got a magnetic field going through that single loop, and we know that if we change that magnetic field, not if it's constant, but if it changes, that we will induce, let's increase the magnetic field into the page, it'll induce a current in that single loop due to the changing flux. So there will be a potential difference that is pushing charges around the loop, right? A potential difference pushing charges around the loop. The potential difference being that one. Okay, then we've got potential difference is equal to minus E dot dl. Now, let's just ignore the signs because the signs takes a little bit of argument. Let's just ignore the signs for a second. So therefore, right, if potential difference is just EMF, if the potential difference that's pushing the charges in this loop, right, in that direction, is just the EMF that's induced by Faraday's law. Therefore, without signs, we can write E dot dl around this closed loop, right? So now it's a closed loop because you can only induce an EMF in a closed loop, is equal to d phi dt. So now the Faraday's law, which is just that a potential is equal to you can induce a potential, right? This is a potential because potential is E dot dl, and is induced by a changing magnetic flux. So what we've shown here, just by combining these two equations, is that a changing magnetic field must induce an electric field. If it induces a potential difference, then it must induce an electric field, right? Potential differences come from electric fields. That's what this equation tells us. Potential differences come from electric fields. So and again, the closed here is the fact that you can only induce currents, induce EMFs, induce potential differences in closed loops. So that's the closed nature. So that's this equation. Now there is a minus sign that we've left out. Now you might say, hey, if I combine top equation with middle equation, the minus signs cancel. But we got to be careful because I said that, let me just find a different color here. I said that these potential differences are the same thing. Well, they are the same thing except for the fact that they're in opposite directions. The potential difference required to push the charges in the direction shown is the opposite of the potential difference that is set up by the field in the second equation. It's a little hard to explain that, but let me try to show that here. So imagine that so here I've got, again, the loop, which is the black circle, and the magnetic field in the middle, which is increasing. And so we're inducing a current in that loop in the direction such that the induced current has a magnetic field that points opposite to the field that created it. So the induced magnetic field points out of the page. So the induced magnetic field points out of the page. So that's how we know the direction of the induced current. An induced current must be pushed by a potential difference that's pushing it. If the induced current is in the clockwise direction, then the potential difference is pushing it in the clockwise direction. So the induced potential difference is like, it's not the same as putting a battery in, but it's like putting a battery in that direction. But think about, in order to push a current in the counterclockwise direction, there must be an electric field pushing, right? Because the current is the motion of positive charges, so the electric field must be pushing in that clockwise direction. So the potential difference must be going down as we go around the loop. So the potential difference, VF minus VI, if you look at any two adjacent points, each adjacent point must have a lower effective potential difference than the point before it, yet the induced EMF has a higher potential difference after in the way that you can see set up here, right? So this potential is lower than this potential, but this potential is higher than this potential. So therefore, E must equal minus delta V. I don't know if that's a little bit qualitative, but it is correct. And so what you end up getting is that there is a minus on here. So again, this equation that I wrote is in magnitude. The actual correct equation is E dot dl is equal to minus d phi b dt. And so that is Faraday's law. This is still Faraday's law. It's still called Faraday's law. We've just replaced the induced EMF with its equivalent of an electric field. In order to have a potential difference, in order to have an EMF, you must have an electric field. So what this form of Faraday's law tells us, again, is that changing magnetic fields induce electric fields. Changing magnetic fields in turn induce EMFs, therefore changing magnetic fields in turn induce currents, but changing magnetic fields induce electric fields. If we go back here then and we replace that equation for potential difference with Faraday's law, E dot dl is minus d phi b dt. And now, notice the other important equation we've left out is the Lorentz force. That's not in here. But these four equations encompass everything but the Lorentz force, right? The Lorentz force. The four equations encompass everything that we've talked about but the Lorentz force. Okay, so now you can see a lot of symmetry going on here. We got an E dot dA and E dot dl, B dot dA and B dot dl. And you can see the similarities between electric and magnetic fields. But there's one thing that's left, which is that you see that a changing magnetic field induces an electric field. Therefore induces an EMF, therefore induces a current. But like right now, I care about the fact that changing magnetic field induces electric field. But what about a changing electric field? That doesn't show up anywhere here. So I do want to take a few minutes and talk about changing electric fields. And that comes into Amperes Law. Amperes Law is not perfect. It does not actually, the way it's written, doesn't hold for all situations. So we pulled the wool over your eyes. There's a modification that Maxwell had to make to Amperes Law in order to put these four equations together and show how they're connected. So the idea here is that these four equations are called Maxwell's equations. They were not discovered by Maxwell, but what he was able to do was he was able to take Gauss's law, Amperes' law, and Faraday's law, put them together and show how they're similar and how they're connected and make some really important conclusions from that. But one of the things he did was he corrected Amperes Law, which is not quite right. So we're going to take some time to correct Amperes Law. So Amperes Law, B dot dl equals mu naught I enclosed. We take that as something which allows us to calculate magnetic fields from current distributions, right? So we can take a wire, and ignore the circuit that I have here for a second. Let's just take a current carrying wire and put an imaginary Amperian loop around it. And so from that, we can say if we integrate the magnetic field around that wire, then the magnetic field must be due only to the current enclosed in that wire, right? So we figure out that there is a magnetic field around the wire from the current carrying wire. Well, now let's take a circuit. Let's say an arbitrary circuit. And I just drew an RC circuit. And say, well, it must be the same thing, right? So the fact that there's a current, if we turn this circuit on, and yes, if we turn this circuit on, we're going to start charging the capacitor, and eventually no current will run when the capacitor is fully charged. But while the capacitor is charging, that is, while the current is changing, right? At some point, the capacitor is going to be fully charged and the current won't change anymore. But while the current is changing, we can apply Amperes Law anywhere and say, oh, well, so there must be a magnetic field around this wire due to the fact that there's a current running through the wire. If there's a current running through the wire, there must be a magnetic field. That means there must be a magnetic field here, and 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 you're getting bored of me saying, and there must be a magnetic field here. But there are and these little dotted circles are just Amperian loops showing there's a magnetic field everywhere. But the funny thing is what happens if I put a dotted loop in between the capacitor plates? Again, while the capacitor is charging. Once it's done charging, there's no current running and there's no magnetic field. There's an electric field between the capacitor plates, but there's no magnetic field if there's no current. But while the capacitor is charging, there's magnetic field everywhere.